So from there, we now want to introduce Bayes' theorem. Bayes' theorem is essentially conditional probability. The probability of B given A. Okay? Now, conditional probability says that the probability of B and A divided by the probability of A. Everybody's comfortable with that, right? You've been using that in your homework. Now we're going to make some substitutions. We just learned that the probability of A is the combination of all these variety of probabilities, right? We said it was the probability of B1 times the probability of A given that B1 happened, plus the probability of B2 times the probability of A given that B2 happened. And obviously we can go on and on for however many B's there are there. Okay? On the top, the probability of B and A. Okay? What is the probability of B and A equal to?
Probability of B by what's the C?
Let's look at our Venn diagram again. Okay, so here's B over here. So B and A is this section over here, correct?
Mm-hmm.
Are we all right with that? Okay, so it's the probability of B, which would be this whole thing, joined with
Probability of A
when not B is true. We could say that it's just the probability of B and the probability of A, right? But we're going to write it slightly different. Can I write this?
Looking at the black.
The black, right? The black is the intersection of A and B. That's what I want on the top, right? On the top here, I want B and A. Okay, so B and A is that black, which I can write in this format, right? The probability of B, which is that, intersecting with the probability of A given that it's inside of B, which would be this section right here. Are we okay with that? So we're going to write that down. Actually, it shouldn't. I guess it should be intersected. It should be times because we don't know if they're dependent or independent. So there we can make our final statement, which is probability of B times the probability of A given B, which that is Bayes' theorem. Okay. Now, with this, we're going to go back to the previous problem. Okay. we're going to ask a slightly different question now. Okay, so we don't need that anymore. We've got Bayes' theorem up at the top. We've got the work that we did before. Let's ask a slightly different question. What is the probability that the two colors were different? So I got a purple and a green. Given that the last one I pulled out was green.
When you pick 2.
So remember, I take 2 out. Same problem. Still take 2 out of A, randomly put it into B, and then I pull 1 out of B. So given that I pulled that one out and it was green, what's the probability that I transferred a purple and a green versus a green and a green or a purple and a purple, right? Because I can get a green regardless of what I transferred over. But the question is, what's the probability that I transferred 2 marbles that were different colors? Getting pretty complicated now, right? These are complicated probabilities that on their own we could reason through, but it would take us a while to think through it. A lot of brain power, a lot of brain juices. But if we use Bayes' theorem, it's going to be significantly easier. Okay? So this, in terms of what we had before, right? This is going to be the probability of PG was B2, right? So this is what is the probability of B2 given that it was green and that was A. Okay, so we're going to use Bayes' theorem. So that's going to be the probability of B2 times the probability of A given B2 over all of that stuff. But remember, all of that stuff there on the bottom was just the total probability of A, right? Which is what we found when we did this question earlier. And so simply now all we have to do, I'll move that up out of the way, we don't need it anymore. So what was the probability that B2 happened? What was the probability that we changed 2 different colors initially?
48.
That was this one, right? The 48 over 90, which we found before. So 48 over 90 times the probability of A given B2, which we also found earlier, right? 2/5 was the probability that we got a green given that B2 was changed, so 2/5, all over the total probability of A, which we found early was 0.36. It should be
592.
593. Which means if I pulled out a green, we got a pretty good chance, almost a 2/3 chance, that I transferred 2 of the same different colors. Okay. Can you see how it could be used? It's difficult, right? Because you have to think of, okay, what are the situations? You may decide that a tree diagram is better anyway because then you can visualize the process. And like I say, the first time I taught this, my students, there were 4 of them at the time, 4 in the class. And of the 4 of them, 3 of them decided that they were just never going to use Bayes' theorem. They were very difficult. They said, can you give us a situation where we would have to use that instead of a tree diagram? And for the life of me, I couldn't come up with one that could be worked using Bayes' theorem that couldn't be worked using a tree diagram. Okay, so if you are very comfortable with tree diagrams, by all means you can use it, especially if you're not very comfortable with the way of writing the terminology and the different probabilities. What I do recommend, though, is that on tonight's homework, you try to use Bayes' theorem. Okay? If on a couple of them you want to use the tree diagram as well, just to figure out which one you feel is easier, then be my guest, right? But I think that if you can figure out how to define this initial question, then Bayes' theorem becomes very easy for the types of questions that they would give you, that they would think of using the Bayes' theorem. Okay? A lot of times it's only a two-dimensional, where B can only be two things, though it states in the syllabus that they can do up to 3 options. Okay? All right. Let's do this. Take a break.